Hello again, and welcome back to the Cedille Cast, a series of videos on writing programs and proofs in Cedille. In the last video, we saw how to derive zero-cost coercions between types using dependent intersections, equality, and a new construct phi that allows you to essentially change the type of one term to the type of another term, provided that these two terms are equal. The obvious applications of zero-cost coercions are zero-cost proof, program, and data reuse, and in a future video we will cover that topic in more depth. But today's video will be about a much more subtle use, using casts to generically derive equi-recursive types using Tarski's Fixpoint theorem. First, a short primer on recursive types. You are probably already familiar with them at some intuitive level, especially if you use languages like Haskell, ML, or many languages with dependent types. For an example, any natural number is either 0 or the successor of another natural number. Any list is either nil or the cons of some data with another list. Note the recursion inherent in the definition of these types. One way to model these and other such types is as the least fixed point of a functor whose parameter is a type representing the recursive occurrence of the type you want to define. For example, natural numbers would be defined as the least fixed point of the following functor. natf our type parameter r represents the recursive occurrence of nat in the functor that we're defining, which is, for all x, I'll leave this blank for now for the successor case. In the usual Church encoding, we simply have an x to x function, but we will be using something called the Church-Scott or Perigo encoding, where our successor function is allowed to take, our abstract successor function, I should say, is allowed to take an additional argument, r. So whereas before, in the Church encoding, this x argument represents the previous computed value through iteration, this r represents the predecessor to the number that we're on. In effect, instead of encoding numbers as their own iterators, the Perigo encoding encodes them as their own recursors. They have access both to the subdata as well as the previously computed value. Now, let's give a couple of example terms to build an intuition here for a type such as this. In this formulation, the terms representing 0, 1, and other numbers actually have an infinite number of types. 0, 1. So one version of 0 has the type for all r, natfr, C, S, Z, as expected, but it also has a type with one additional level of nesting of the natf functor. Here in our context, our abstract successor case, S, is a function that takes two arguments, a natfr for the predecessor, and x for the previously computed value, and is supposed to return x. For 0, we still only need to return z. Compare this to the definition above, where in our context, with one level of nesting of natf fewer, S has type r to x to x. Similarly, 1 has one type, natf of natfr, to think about how we would go about defining 1. We know that it must be the successor of 0, so at least one application of successor. Here we need to provide, as a first argument to S, a natfr, which we have defined here, 0, 1. 0-1, I should say. And then we need to provide it the previously computed value, which of course is the base case, the abstract z. One also has this type, natf, natfr. And it's easy to see that because 0, 1 and 0, 2 are equal, 1, 1 and 1, 2 are equal. In fact, we can witness this with the following qualities. Zero, 1 and 0, 2 and are equal by beta reduction, and 1, 1 and 1, 2 are equal by beta reduction. So it should be clear that the term 0 has an infinite number of types representing any number of nestings of the functor natf. Similarly for 1, 2, and all other numbers. So the most accurate type for the natural numbers would be the limit of nestings of natf, or the fixed point of the functor natf. Cedille does not have built-in support for defining recursive types, but thankfully, with Tarski's fixed point theorem, casts, and a little bit of impredicativity, we are able to derive them. The first thing we need in order to translate the theorem to the type theory of Cedille is some notion of monotonicity, as Tarski's theorem applies for monotonic functors. In mathematics, a function f is monotonic whenever we have x less than or equal to y, then f of x is less than or equal to f of y, for some notion of less than or equal to. Fortunately for us, thanks to the previous video, we already have an adequate notion of less than or equal to, casts. To give some intuition for this, a cast represents a proof that every term of type x can also be viewed as having type y. If we think of types as denoting sets of terms, then you can also think of this as the set of terms typable by x is contained within, or is a subset of, the set of terms typable at type y. This is a perfectly good less than or equal operation, partial order on types, casts between x and y. Therefore, our definition of monotonic is as follows. Monotonic is a property of type schemes f, which is for all x, for all y, if there's a cast between x and y, then there's a cast between f of x and f of y. Nope. The next bit of kit that we need for the theorem is a notion of an F-closed type. Here, we say that some type A is F-closed means that f of A is less than or equal to A, or that there's a cast from f of A to A. F closed is a relation between a type scheme and a type, F and A, which is the existence of a cast. Let me just copy that. No, didn't quite work. We're now almost ready to define our candidate type constructor fix as the greatest lower bound of the set of all f-closed types. Fix f will be our fixed point of the functor f. However, we need one more thing, a notion of a meet or a minimum in order to calculate this greatest lower bound. Because if we can find the meet of our set of f-closed types, and show that it is a minimum of that set, it is necessarily the greatest lower bound. Perhaps surprisingly, universal quantification is exactly what we need here. Again, viewing types as denoting sets of untyped terms, you can think of universal quantification as being a kind of intersection over a family of sets. And intersection, of course, is a very intuitive meet operation for sets, especially when the partial order is subset. For example, consider the empty list, nil. Here we'll just use the regular old church encoding for brevity. Nil, the empty list, can be seen as both a list of net and a list of bool and a list of unit. In a sense, it's in the intersection of the type family of lists of A. So, that being the case, let's define our type fix of f as being the intersection of all types A, predicated on the fact that A is f closed. So let's take a moment to recap what we've done. So far, all we have are some definitions translated into type theory from Tarski's Fixpoint theorem, and a candidate fixed point of f as the greatest lower bound of the set of f-closed types. We have not yet shown that fix f is indeed a fixed point, but that's what we will do next. First, we need a lemma stating that fix f really is a lower bound, or an infimum, of any f-closed type. As to say that for any A, if A is f-closed, then fix f is less than or equal to A, or there's a cast between fix f to A. Let's call this cast fix. And for any f and A, if A is f closed. Then there exists a cast from fix f to A. Call it FC for the evidence that A is f closed. Here we must produce a cast, so we will use our constructor intro cast, which takes two arguments. The first argument is a function from fix f to A. The second argument is a proof that this function behaves extensionally like the identity. Here, in our function from fix f to A, we have a fix and must produce an A. This is easily done because fix was defined to be in the intersection of all f closed types. And since A we have already by assumption is f closed, we simply instantiate fix to the f closed type that we want and give it the proof that this type really is f closed. Note also that if I use Control-I in and look at the normalized, the erasure of this term, this is equal to the identity function. Therefore, the proof that this function behaves extensionally like the identity holds simply by beta. Now we are, with this lemma done, we are finally ready for the two main parts of the proof. To show that fix f really is a fixed point of f, we need to show that fix f is less than or equal to f of fix f, and to show that f of fix f is less than or equal to fix f. If we show both of these, then what we have shown is, in a sense, that f of fix f is equal to fix f. This first case we will call cast in fix, and it represents the in, or rolling of the recursive type for all f. For any f that is monotonic, there is a cast from f of fix f to fix f. We need to introduce a cast again. The function must have type f of fix f to fix f. Here we will introduce a let binding. Call it f and provide this as the first argument. We have, by assumption, an f of fix f, and we must produce a fix f. To construct a fix f, we look at its definition and show that we must have a way to inhabit any f closed type. So, given some arbitrary f closed type A and a proof that is f closed, we must be able to inhabit A. This proof takes a number of steps. The first thing that we would note is that because A is f closed, by definition, that means that we have a way of converting f of A to A, casting f of A to A. Our new goal is to produce an f of A. Because f is monotonic, we know that we can produce an f of a from an f of something else, provided that there is a cast from that something to a. What can we convert to an a? Thanks to our lemma, cast fix, we know that we can convert fixf to an a. It needs the proof that a is f closed, not monotonicity. And finally, we need our term f of fixf, which we have by assumption. Since all we have done is change together two casts, the term that we have defined, f, is again, or erases again to the identity, and so the proof that it behaves like the identity function holds by simple beta reduction. That is our in. Let us now define out. A cast from fixf to f of fixf. Again, defining our function in a let binding. Here, our function f of type fixf to f of fixf, we must produce an f of fixf. The way that we can do this is by noting that f of fixf is itself f closed, and fix is a term which inhabits, can be instantiated to, I should say, any f closed type. We must now provide proof that f of fixf is f closed. To make this a little bit more clear, let's use Control-IT when we're hovering over this hole right here to be able to interactively normalize the expected type. Control-IN, this is normalized maybe a little bit too far, so I will Control-I equal to rewrite it. This should be read as a cast of f of fixf to f of fixf. Again, thanks to the monotonicity of f, we can derive this cast if we can derive a cast from f of fixf to fixf. But of course, this is exactly the type signature of the term we defined above, cast in fix. Also, again, since all we've done is use type instantiation and casts to prove that our function f behaves like the identity function, holds by beta reduction. Great. To conclude this video, let's note that these really are, thanks to the runtime behavior of casts, these really are equi-recursive types. The same set of terms inhabits fixf and f of fixf. So to show the two computation laws that establish this, let's define some helper functions in fix. And outfix whose types are simply the usual types that you would expect for recursive types. In takes an f of fixed point and returns the fixed point. And out takes the fixed point and returns f of the fixed point. Outfix x is equal to x by beta reduction and infix x is equal to x by beta reduction. That concludes this video. I don't know yet what the topic will be for the next one, but hopefully it will be out early next month. And until then, hope you enjoyed this one, and Happy New Year to you all, and see you next time.